All right, so here we are. So, right, the exam is on Monday. I will be available during our product session for further questions. If people have them, come by, we can have further discussion. Right, so again, the material on the exam is through Electromagnetic on magnetic radiation and through problem set 9. Okay. So, the exam is, I made the exam, it's 3 problems. And I'd say, if you're doing really complicated math, you're not doing it right. So that's a hint. I mean, the problems should be fairly straightforward to do. They're more conceptual in nature. Concepts could be challenging. They're, it's not going to be a breeze, but it's not like, oh my God, I've got to do this massive, piece of math. If that's where you're going, then you're not doing it right.
Yeah, so with the previous exams, feel like a good indication?
Yeah, I mean, if you look at the solutions to the exams, you'll see that it was pretty straightforward to do. It's not clear what to do always, but if you know what to do, it's like 1 or 2 lines of math, right?
Yeah, it's not clear until like the last 5 minutes.
Right, that's right. But so they are an indication. Okay, so that if it's that level of detail of complicated mathematical solutions. So it's in a similar spirit to the previous exams. Okay. All right. So let's just sort of wrap our brains around. I think it's hard. This has been it's an intense semester. There's a lot of material covered, and kind of got it. Roll back and think about where we started and where we been. So I would say if we sort of divide up what we've studied. I would divide our subjects in the following way. Okay. So these are the main subjects we've studied. All right. And of course, everything, begins with Maxwell's equations, but the ideas of thinking about statics, in electrostatics, we're thinking about the situation where the charge density is not changing, and also the current is 0. Okay, so we're thinking about static charge densities, and the basic equations of motion we have are Gauss's law and the fact that the curl of E is 0 in electrostatics, right? So, what the goal often in electrostatics, before I say what this tells us is that the electric field itself is the gradient of a scalar, and in its connection to potential energy, we write it as minus the gradient of the scalar potential. Okay. So, goal in electrostatics is often to determine what the electric field is given the charge density, and that is often done in saying, what is the electrostatic potential? And then once we have the potential, we can get the electric field. And as we discussed, you know, there's a famous Steve diagram which connects these players, the charge density, the electrostatic potential, and the electric field, depending upon, so, you know, I might have the charge density and I want to find the potential, or I might want to find the electric field, and all of these things go back and forth from one another through these various equations, okay? And we have the general solution, so maybe I'll do one thing at a time here. That these two equations together give us the Poisson equation, which tells us, if I look at the divergence of this, I get that the Laplacian of phi is minus 4 pi rho. And when this equals 0, we call it Laplace's equation. So at positions where the charge density is 0, del squared phi is 0, that's Laplace's equation. And the general solution to this equation is so this is a general solution to the Poisson equation, where we can add any function that satisfies Laplace's equation, and this can be chosen to set the boundary conditions, okay? Now, if we take into account all the charges in the problem, and there's no charges at infinity, then typically we'd take this to be 0, right? We include this kind of equation where we might want to solve a problem where, for example, we have a charge distribution near a conductor, and instead of calculating what all the charges are on the conductor and using this equation to calculate it, we can set the boundary conditions based on Green's theorem, right? So we can solve the general problem based on Green's functions. Okay, and we did some problems of that sort. Now, we also know that sometimes it's easy to go directly from the charge density to the electric field using Gauss's law, using the integral form of Gauss's law when we have special symmetry, right? So this equation tells us that we have this surface integral over a closed surface of the electric field. That's the integral form of Gauss's law. And when the electric field is constant, or when this is constant on a surface, then we can bring it outside the integral, and solve for the electric field very simply by then just finding what the charge that's enclosed in that surface and dividing by the surface area. And we can do that based on symmetry conditions. When we have spherical, or we have cylindrical, or planar-like systems, we can use symmetry arguments to tell us, right? So, and those are very special problems. But when we can use that, we definitely should, okay? Now, we also spent a lot of time this semester thinking about multipole expansions, okay? So, and by the way, interrupt me at any point, okay? Yes?
And what was the situation you said we could use Green's functions?
Well, we can always use a Green's function, but we typically would use a Green's function. So let's just remind ourselves of, a problem like, if we had, say, a conductor, say we had a grounded conductor, and we have some charge density near the surface of a conductor. And I want to find the electrostatic potential at some point here, okay? Now, in principle, I could use this equation if I have the charge density here and the induced surface charge here, and calculate the potential by adding up all the effects from all these charges. But that's a very tedious way to solve this problem. Instead, we can use the boundary conditions and find the Green's function for this problem, that satisfies the boundary conditions without actually calculating what this is. Okay? So those are things you should review, because it's been a while since we thought about it.
What category would that fall under? Is that quasi-statics?
No, that's statics.
That's just statics.
It's just statics.
Okay.
I mean, nothing's moving here.
Yeah.
Okay, just static, it's just electrostatics. Okay. The multipole expansion. We had the situation where we have some charge distribution that is localized within some region. And here's the origin. And the point of observation is over here. And the distance from any point in the charge is, it's always good to remember this geometry. We have the points of the charge, and then script the r, which is the distance between the point of observation and the charge. And the multipole expansion was a situation where we're far away. So it's saying that this distance from the origin, r, is much, much greater than d, where d is, say, this, okay? And under that circumstance, when we're far away, we were able to do a Taylor series expansion of the potential and see that there were different terms that dominated, right? So how does that go? So what's the dominant term if I'm far away? Q over R, right? The potential falls off like 1 over R. The electric field falls off like 1 over R squared. It's good to remind ourselves about all of these things for a point charge. So for a point charge, so this is not necessarily a point charge, but if I'm far away, it looks like a point charge because I can't see the distribution. So Q, what is Q? How is Q defined? Q is the monopole moment. And how is it related to the charge distribution?
Total charge.
The total charge. And so I would get that by integrating over the whole charge distribution. Or equivalently, if I have a bunch of point charges, summing over all the point charges, if they're point charges, right? So that's the monopole moment. And if there's some net charge, then this is the dominant term. But suppose it was a neutral distribution, had an equal amount of positive and negative charges. What's the next order term? The electric dipole term. And how does that go? What is the electric? I'll give you these on the promise. You don't have to memorize this stuff. But what the heck? Firstly, how does it fall off with distance? 1 over r squared. And it depends on the electric dipole, which is a vector, right? So what is the potential? P dot r hat. And P is the electric dipole moment, which is a vector. And it's given by the integral over all the charges. I mean, I don't have to call these primes because there's only one integral, but it's related to, as we've said, how do we intuitively understand what the electric dipole vector is? It's exactly something about the separation of the positive charge from the negative charge, right?
If the average position of the negative is the same as the average position of the positive, then.
Right.
dipole.
That's correct.
Yeah.
So it's sort of the net positive charge times the average position of the positive charge minus the net amount of negative charge times the average position of the negative charge. So if you know what that is, you know what the dipole moment is. How are they separated from one another? And then the next term goes like 1 over r cubed, and that's the quadrupole.
Everyone's favorite tensor.
Everyone's favorite tensor. Q is a rank 2 tensor. P is a rank 1 tensor, known as a vector. And Qij is equal to the integral over the charge distribution times something that is related to a second order polynomial. So the notion of moment comes from thinking about the moments of a distribution. If I think about a probability distribution, one talks about the moments, right? What is the mean, the variance, the skew, the kurtosis, all these things that you may or may not have heard of from statistics are the moments. So they represent these are polynomials, and this is xi, xj minus r. If I got this correct, I have to check. I don't know if there's factors of 2 in there that I forgot. I'm glad you guys remembered that. It's awesome. Yeah, makes me happy. Times the charge. I drilled things into your heads. That's crazy. All right. So, and so forth and so on. Okay. So the moments are properties of the distribution, and given those moments, we know what the potential is far away. These are known as the Cartesian components of the moments. There are also what do we call the spherical components of the moments. In particular, so we can also write this in terms of the spherical harmonics. Where these guys we obtain by projecting the charge distribution onto an orthogonal polynomial related to this distribution. Yes?
So concerning the constant for this y then, will it be given or we need to memorize it?
I'm sorry, I can't quite hear. Can you repeat the
All the
question?
constant for the y then, we are so using the y then, all the constant for y 10, 0, 10. So what
Yeah,
is
so
constant
for each
given?
For each YLM, there is an appropriate moment.
He's asking if we need to memorize the YLMs.
Oh, I'm sorry, I didn't understand the question. Of course not. Yeah, no, that's not the point, no. I'm sorry, I didn't understand the question. So the QLMs we obtain by integrating over the distribution, which we would write in spherical coordinates. And then we multiply this like that. Okay. And there are relationships between these different components, the spherical and Cartesian components. But I wanted to remind you about one other thing about when we have particularly when we have azimuthal symmetry. So if we have a charge distribution of some kind that has azimuthal symmetry, is independent of phi, then we have a more simplified version of this because it's related to the Legendre polynomials, right? So let me try, yeah. So then we could write in that situation, the potential in that case would only be a function of r and theta. It would be independent of phi if rho is only dependent of r theta and is independent of phi. And that expression we can write where these are the Legendre polynomials. And the QLs in that case are related to the projection because when m equals 0, these things are related to the Legendre polynomials. And you'll remember that this, in this case, this is related to the z component in Cartesian. Okay. Now, one of the, yes?
The phi, so if we're dealing with phi is, or it's metric in phi here, generally the phi would just show up as a phase factor in the YLMs, right?
It would.
Okay.
It would, in the YLMs, they're like associated Legendres times e to the I m phi.
Okay.
That's correct. Okay, but a point I wanted to emphasize here and remind you of, so this is the z-axis, okay? So when theta equals 0, r equals z, if z is greater than 0. Okay, so up here, at theta equals 0, this is r, which is the z coordinate. Everyone with me? So at theta equals 0, that's the potential on the z-axis, which is equal to QL over RVL plus 1, PL of cosine of 0, which is PL of 1. right? Because cosine of 0 is 1. And all the Legendre polynomials at the origin are 1. So this is equal to this. So if we know the potential on the z-axis, we know it everywhere. Why? Because if we know it on the z-axis, we can write a power series and we can find these QLs, and once we have the QLs, we just plop it in here and we know it everywhere else. Okay? So that's something we did, right? We had those disks, and then, you know, we had to integrate the disks, and we found that, we did all that stuff. Review that. Okay? Very good. All right. Magnetostatics. In magnetostatics, now we're looking at the case still where the current, where the charge density is constant, but there can be current. It just means that the current is steady, because we remember that charge conservation, the continuity equation, tells us that this is always true. This is conservation of charge. In magnetostatics, we're looking at the case where del dot J is 0, which is mean the current is neither converging nor diverging from any point of space. It's just flowing in a smooth way. Not a smooth way, but a way that the current doesn't converge or diverge, which means that we have a piece of charge density that's everywhere, constant, like in a wire, okay, where we have a constant flow of current. In that situation, we have the equations del dot B is 0, and del cross B is 4 pi over C J. And the fact that del dot J is 0 is consistent with this equation, because if we take the divergence of the left-hand side, we get 0. So this is true only when this is true. Otherwise, we have the displacement current to come back to. Okay? And so, again, we have this equation implies that we can write B in terms of potential, which is the vector potential. And the divergence of A is irrelevant, and we typically choose that in magnetostatics to be 0. Okay? That's it. We can set this any way we like. If there's no other reason to choose it in any other way, we just set it to 0. And that together then tells us that the different components, Cartesian components of the vector potential satisfy a Poisson equation. Okay? So in the same way that we had for the scalar potential, we have the vector potential satisfies this plus some other constant field, as long as this satisfies the Laplace equation, or whatever you want to call this. Different. Okay. Where the curl of this is 0. Typically, we don't worry about that. Now, these problems are kind of horrible because we have to integrate over vectors. Yeah?
You said the Poisson equation is only the case when we choose that particular gauge.
That's correct. Otherwise, well, how do we get from here to here?
EAC minus AEC.
Close, yeah, right? I mean, I have to plug in B as the curl of A. So this is really equal to the gradient of the divergence of A minus the Laplacian, right? Which is this only when you set that to 0. Yes?
Is that x plus x prime in the denominator there supposed to be x minus?
Yeah, it should be a minus, of course. Yes, thank you, sorry. Right. Now, magnetostatic problems are hard because they have all these vectors in them, but they are what they are. As we know also, in the same way that we have for Gauss's law, if we have symmetry, we can use the integral version of this using Stokes' theorem. And if the magnetic field is, this has got some tangent vector dl around some contour, then if B dot into the tangent vector is constant, we can take it outside the integral in the same way that we do in Gauss's law and solve for the magnetic field when we have symmetry. So then we can take B dot, the tangent vector, outside the integral, we get and this is some length, and then we've solved for the problem. So, you know, this is how you solve for the magnetic field around a wire. Yeah.
Am I right, and sorry this is jumping the gun a little bit, but am I right in saying that the primary difference between this and quasistatics is that we don't have a lot of these equal to 0?
Yeah, we'll remind ourselves of quantizatics in a moment.
Okay.
Yeah.
Sorry.
Yeah, we'll get there. All right. So, so we have a similar kinds of equations here. Now we also think about the multipole expansion. Or magnetostatics. So again, we do the same thing that, where is it? Well, I guess, yeah, what's here? I erased that part of it. That we did in electrostatics in the context of magnetostatics. So now we have some currents that are flowing around. And, you know, we want to know what is, in this case, the vector potential and thus the magnetic field at some point when we're far away from the origin, okay? And so we can do the same kind of Taylor series expansion that we did for the electrostatic potential, for the vector potential. What's the dominant term? Dipole. There is no magnetic monopole. So the first dominant term is the dipole. And that has the form of r hat crossed into m over r squared plus dot dot dot. I mean, magnetic quadrupole, etc. We didn't even go there, okay? And the magnetic dipole moment is similar to the expression for the electric dipole moment, but everything's got a cross product in it. So M is the integral over this x crossed into the current. It's actually over 2. Okay. again, you don't have to memorize any of these things, I promise you. And, yeah, okay. So, moreover, if you remember, suppose I had a current loop or some planar loop of current. What's the magnetic dipole moment associated with that?
I times A?
It's I times A, in these units over C. So this is 1 over C, the current, the area, and we call it, to not confuse it with this, I'll call it script D, this is the area. And what's the direction of it? It's a vector. In the normal, using the right-hand rule. Okay. And the magnetic field is equal to the curl of the vector potential, and it's the curl of this. Now, what we showed at some point that this is actually also equal to that, which is the electric field, this is the magnetic field of the dipole. The electric field of a dipole is minus the gradient of the scalar potential of the dipole. So they have the same form. The electric field of an electric dipole is the same as the magnetic field of a magnetic dipole. All right? Question. How does the field fall off as a function of distance for a dipole? One of our, yeah, cubed, yes.
Should that be a cross product of the magnetic dipole?
No, interestingly. So this is
Oh, 'cause we took the curl.
equal to the curl of that. But that, with a little bit of algebra, equals that. Okay? We call that the sort of the pseudo potential. Okay, so it falls off like 1 over r cubed. And what is the actual form? How do I take this gradient? Well, you know, I can screw around with spherical coordinates and whatnot, but the easiest way really to do this is with the Einstein summation convention. Everyone's favorite. Right? So I gotta write this, so I can write this as minus the gradient. I'll multiply this top and bottom. R cubed. Okay?
Yeah.
So how do I take the gradient of that? Firstly, I wrote this all in terms of, so because I don't have to worry about r hat. All right, now I have, so I'll write this as, so I'll look at the, let's look at the ith component of this field. So that is partial respect to I of that, right? So that's the ith component. And now how am I going to take this derivative?
We need to write out the dot product.
We're going to write out the dot product in terms of the summation convention. And don't use the same dummy index. Don't be a dummy. Sorry, I shouldn't use that. Okay, and now what?
Right, R?
So I'm going to use the, first of all, the PJ is a constant, is not varying with the position of observation, so I can take this outside. So I have minus PJ partial J of xj over r cubed. which is equal to what? It's equal to Pj, oh, this is I, di of xj over r cubed plus xj partial I 1 over r cubed. Everyone with me? Using the product rule. What is this derivative? Quantic or delta? This guy, di 1 over r cubed, is equal to minus 3 over r to the 4th partial respect to I of r, using the rules of derivatives. Right? I mean, calculus, man, you just gotta do it. It's gotta be like writing English. Okay, so now this partial derivative is r hat. It's the direction. There's lots of ways to do that, but the gradient of r is r hat. So putting that all together, what I get is this is equal to the electric field. Let's see, I got the minus signs, I get these 3's. So I have minus P over r cubed plus 3 r hat times r hat dot into P over r cubed. So that's the electric field associated with the dipole. When P is along r hat, it's equal to 2 times the magnitude of P. If it's perpendicular to it, it's, right, so we have the electric field associated with the dipole. What's the magnetic field associated with the dipole? We know a magnetic dipole. It's exactly the same, but M is equal to P. All right, let's see. Quasistatics. When we did quasistatics, what we're talking about now is a situation where we have a changing B field. Okay? We can have a changing B field because, for example, we might have a changing current. And when we have a changing B field, we know that that means that the curl of E is no longer 0. And this is Faraday's law. Okay? So we might have, for example, let's say we have an AC current and it's attached to a solenoid. Then we're going to have a magnetic field that's a function of time. And we're going to then have electric fields that are generating the so-called back EMF, right? So there is the electromotive force this is the flux of the magnetic field through the surface that is enclosed by the contour. Okay. Now, what makes this quasi-static as opposed to just dynamic? Slowly changing. And what it means, so when we think about quasi-statics, we can still have Ampere's law. We know that the exact equation is this, right? There's the displacement current. And E will change because as E is changing, because if B is changing, E is changing. And so there is a term here, but if we can neglect it, if this is negligible, we call it quasi-statics. So when we're looking at a problem like this, where we say, oh, I have a solenoid and I have an AC current and I want to know what the fields are, if I solve this by neglecting this term and just say, well, it's like it's a static magnetic field solved by Ampere's law, but now just B is changing, okay? Then that's the solution that's quasi-static. Now, under what conditions, Colton said this correctly, that is slowly varying, but slowly varying, what is it, is slowly varying compared to what?
Something related to C, probably?
It's something about C, right? Because C is in here, right? What it's saying is that if there's a time scale of change, then we want this to be much, much smaller than what? Or big. It's got to be, the T has to be big. It's it's a long time. It's C times, or I should say the other way. It's the distance, the time it takes light to travel across some distance L. Where L is the size of the system. Of the current distribution. Okay. Or said another way, CT is much, much bigger than L. Okay. Now that we've studied all of E&M, we understand what this means maybe a little bit more deeply.
Target type?
So this is saying something about the nature of the solution that we're looking at is actually, so, okay, let me step back a second. What actually happens when I connect this solenoid to this AC current? What's gonna happen?
Charges just start moving?
They're gonna oscillate back and forth. And what happens when charges oscillate? They radiate. So when we're talking about this condition, we're talking about two things. One, that this is true, that we have slowly varying currents, but there's more than that. We're also saying that when we're looking at this field, we're only looking at it in regions of space that are in the near field. So quasi-statics is also related to what we call the near field, which is to say, if I'm looking at the field at some position x and time, that the position I'm looking at is a distance that's much, much less than CT. I mean, the near field, yeah.
Would it be fair to say that the quasi-static analysis is a way to sort of skirt around using the retarded time? So like, this is when the retarded time is negligible?
That's correct.
Yeah.
That's part of the story. One of the part of the story is that the retarded time is negligible for exactly what you just said. But in addition, there's another condition, which is that we're only asking about the fields in the near field. If we start looking at this far away, when we start going at distances, and remember, say let's suppose we come to this problem where t is, let's say, the period of oscillation. Right. This is saying that we're looking at this field near the solenoid at distances that are close compared to the wavelength at which this thing would radiate. So the quasi-static condition is also saying we're only, that one, it is quasi-static, and B, we're only interested in the solution in the near field. In the near field, which is to say we're looking at distances that are close compared to the wavelength at which this system would radiate, what we're saying is it looks like a static dipole, and I just replace everything in this formula that I just wrote. It's the static solution just changed as a function of time. So it would look like an oscillating dipole, static dipole. Okay, good, excellent. So yeah, that connects some of the stories of things we've discussed together. A couple of other things that I guess I haven't mentioned that we should talk about is force, energy, momentum, angular momentum. So, and conservation laws. We know, from a kind of empirical perspective, we have this notion of action at a distance. The force that is exerted on one charge is affected by a distant charge. But in our modern conception of that, over the last 200x years, we think that there's actually a local interaction. The local interaction is between the charge and the field. And the fields are produced by the charges and the currents, okay? And what that means is that things like that are conserved in the universe, like energy, angular momentum, are transferred between the charges, the matter, and the fields. And then the fields can transfer that back to the charges, right? And so we looked at a variety of these kinds of conservation laws, thinking about what the equations of motion were, what the forces are on charges and currents, and how Maxwell's equations tells us then how energy and momentum and angular momentum are transferred between them. Okay, so of course we have the Lorentz force law. And the Lorentz force law says, have a point charge, then the force on the charge is equal to the charge times the electric field at the position of the charge, and it's related to the velocity of the charge, right? Or more generally, if I have a density. So the other thing we understand is that, you know, the work done by the field on the charge, or I would say the rate at which work is done, is equal to Q times R dot, or X dot, or V dotted into the electric field. The magnetic field does no work because the dot product of that with that is 0, right? And from that, the work that we saw that the charges, that the fields do on the charges, we can think of minus that as the rate at which, you know, work is done by the charges on the field. Of course, this can also be written like this. And so minus J dot E is rate at which sources do work on fields per unit volume. And from Maxwell's equations, what did we find this was? It's change of energy. So this was equal to the so this is the continuity equation, or Poynting's theorem, for energy. It says, so U here is the energy density. S is the energy flux density. And this says that energy flow in the fields can be either created or destroyed depending upon J dot E. J dot E is positive, energy can be dissipated. That's what we call ohmic heating. We can also have energy created if we do work against the fields in a way we can get electromagnetic radiation. Okay? And we had the conservation of momentum based on the force equation, where we had the Poynting vector telling me something about the momentum density, and everybody's favorite, Maxwell's stress tensor, which tells me about the flux of momentum. I promise you there won't be a problem on the stress tensor, so don't stress yourself out on that. Stress yourself out on other stuff.
That's probably the reason there's not a you won't be able to do that.
Yeah.
Very good. All right. Let's continue. So we spent a lot of time talking about electromagnetic waves. Electromagnetic waves both in vacuum and in media. Okay? So if we look at the microscopic Maxwell's equations, everyone should be able to write down Maxwell's equations in this course, okay? Even in CGS units. Okay. All right, so we have the microscopic Maxwell's equations, the Max equations, and if we're in free space, also known as vacuum, rho and J are 0. And so we can, from that we have, this is 0, and we can get the wave equation. How do we derive the wave equation from Maxwell's equations? Take the curl and the curl. Okay. Oh, I pressed out the wrong key. It's like, this isn't right. And similarly for B. Okay, so we have the wave equation. Okay, and we have, if we have monochromatic fields, then we can always write the fields as the real part of a complex amplitude for a given frequency. And similarly for B. Which tells us every time we see a d by dt, we replace that by minus I omega, and that gives us that. Okay. And similarly for B. Now, I want to remind you that the wave equation, we have solutions, but we still have Maxwell's equations, which make constraints between what the nature of the electric field is and how E and B are related to one another, okay? So if we have a monochromatic field, well, we still have del dot E tilde is 0, del dot B tilde is 0. We have del cross E tilde is I omega over C B tilde, and del cross B tilde is equal to I omega over C B tilde. Everyone with me? So this tells me that once I know E, I can always find B. Now, some of the relationships that are specific for plane waves are not true for other waves, okay? But this is true for monochromatic fields. So this tells us that B is minus IC over omega del cross E. So once I know E, I can always find B through this equation. And vice versa, okay? Now, the specific case of plane waves, is where we say the spatial dependence of this thing is something which has the amplitude that's the same on a plane perpendicular to K. Okay? So, we have a plane wave, we have a dispersion relation. What is a dispersion relation?
Describes how K changes with respect
It's the relationship between K and omega. Okay. So how do you find the dispersion relation?
to wave equation.
You just plug in this into the wave equation, or Helmholtz equation, right? So if I plug this in, when I have this kind of form, when it tells me wherever I see a del, I replace that by multiplication by IK. So what does that tell me? It tells me, firstly, I have the dispersion relation, I can plug that in, del squared becomes IK dot IK, or minus the magnitude of K squared. So when I plug that in, I get the magnitude of K squared times minus sign, omega squared over C squared, E tilde is 0, or the magnitude of K is equal to omega over C. So that's the dispersion relation in vacuum, okay? We have other things that are true relating to the plane wave. We have this equation. What does that tell us about the relationship between B and E?
Tells us that.
Well, I can plug that in. It says B tilde is equal to minus I C over omega I K cross E tilde. Everyone clear? So this tells me that B tilde is C K over omega cross E tilde, or K hat cross E tilde. So the relationships between these guys follow. Now, when we have matter, so we might have and what I suggest we're going to do, I'm going to finish this, and tomorrow we'll do the last part of the review on radiation, because we got 5 more minutes. And I want to make sure you guys get enough time to absorb this and review. And you can come with other questions tomorrow as well. So there, we broke up the sources into free sources and things that were bound in the molecules and solids, right? And similarly for the current, although it's a little more complicated for currents because there is bound current and there's magnetization current. So there's free current plus the bound current plus the magnetization current, which typically comes from the spin. It's a kind of complicated story because there is an essence of magnetic fields that are purely quantum mechanical in nature. And when we did that, we got the macroscopic. Which we wrote in the following way. Where D was equal to E plus 4 pi P, where P is the so-called polarization. Oh, yeah. And maybe I need to go back. There's something else I forgot to talk about for free. Come back. The other notion of polarization. Come back to that. Which is the electric dipole density. And H is B minus 4 pi M. This is known as magnetization, which is the magnetic dipole density. And the bound current is the changing, oscillating dipoles, okay? So, what we'll do tomorrow is review waves in matter, and we'll also review radiation. And I want to remind you about the other story of polarization. The polarization of the field, linear, elliptical, circular polarizations, other things you need to think about and review. So we'll do all that tomorrow. Yes?
Where did the curl of, was it magnetic moment show up?
Yes. Oh, yeah. So the magnetization current is the curl of M. So when we break up the current into these three components, this contributes to the displacement current, and this contributes to H. Yes?
I had a question going back to quasistatics.
Yes.
The CT much greater than L.
Yeah.
So when I look at Maxwell's equations, they're local equations, and I have a hard time seeing how this like length scale translates to we can neglect this term in Maxwell's equations. Like I'm just not.
Yeah, it's not in Maxwell's equation, it's in the integral. So when we do the way, if you remember the way we did, and we'll review this tomorrow, so the general solution, for example, for the vector potential or the scalar potential.
Sure.
So this is the solution where the field that I see at some space-time point is related to what the sources were at a space-time point that's related to the retarded time. Okay? But then the question is, can we do a Taylor series expansion of the source term depending upon how the distance, so I have, I have 2 points in space. Both of them contribute to the field at this point. The question is, how big, what's the difference in these retarded times compared to the time over which this changes? So there's a delta t retarded time, which is equal to, delta x prime over c. Okay, so this is related to where the charges are, and this is the difference in the times, the retarded times. The question is the difference in the retarded time big or small compared to the time scale over which this changes? And when this is a function of the retarded time, the question is, I'm going to do a Taylor series expansion of this thing, and whether that Taylor series expansion converges or not depends upon whether this is a small parameter or not. So what I would suggest doing to get your head wrapped around that is look at lecture 19A, where we very carefully looked at the case of the dipole and saw how that Taylor series expansion happened. So there are different time scales in the problem. One time scale is how fast is this charge distribution changing? It might be oscillating, so there's a certain period. But there's another time scale, which is how long does it take light to go from one side to the other? And the comparison between those different time scales will determine something about the nature of the radiation.
So I remember us doing it for a dipole. Is it, I don't need you to do this, but is it just generally true that it will be for any...
So if you go back to those notes, you'll see we ultimately did it for the specific case of a dipole, but it's a more general expression. If I have the charge density, the current density, the question is, I have this as a function of time plus some delta t. The question is, can I make this expansion or not? And that's a question of how fast this thing changes compared to delta t. Is this a good approximation or not? So it's a question of how fast is this changing compared to delta t. Delta t here is the difference in the retarded times, and whether I can make this expression is a question of how big this derivative is. So the comparison, there's the time scale over which this changes, which is related to its derivative, and this. And that's where it's coming from. All right, we will continue our review tomorrow. Have a good rest of your day, everybody. Yeah. One second.